Hi everyone. So I'm Einig. I'm a second year PhD student in IRAM Grenoble, and today we'll focus more on the uncertainties on the observations, and we'll talk about the problem of applying hyperspectral imaging method for signal extraction for noisy line cube and their problems. So the data I'm using are taken from the RMB dataset, which is composed by several line cubes with several line cubes. For instance, here you see certain CO is 17O, which have a large field of view and 240 velocity channels. And one important thing with this data set is that it has an important diversity of signal-to-noise ratio. For instance, Atelier has a very good signal-to-noise ratio. It's easy to segment the pixels which contain signal and pixels which are devoid of signal. And it's not the case for C17O. And so we have an important uncertainties on the pixel values in function of the different line cubes. And it can cause problem because for my part, I'm using some machine learning algorithm. And the problem is that if the input have uncertainties, that means that the model parameters have uncertainties too, because the uncertainties will propagate through the models. So we have two possibilities. The first one is to modelize the impact of the uncertainties in the models and to constrain it. And the second one is to try to denoise the signal. That means to increase the signal-to-noise ratio in order to decrease the error bars. So in signal processing, hyperspectral signal processing, there are a lot of methods in order to do that. But I will focus on a particular one, which is based on the low rank assumption. What is the low rank assumption? In fact, this is an assumption which says that it has an important redundancies in the signal, and that we can exploit these redundancies in order to extract signal and to decrease the noise level. So, for instance, we will process here it's a time coded neural network, which is a great representative of this kind of methods that are based on these low rank assumptions. So we'll process the pixels one by one. And here, every input is just a velocity channels. And so these are the intensities. We will try to compress those intensities in what is called a bottleneck theta, which has a dimension which is really lower than the dimension of the input. And then we'll try to reconstruct fidelity the intensities, but because of the compressions, we hope that the signal will be nicely reconstructed, but that the noise will be reduced or even lost. More mathematically, that means that we're looking for those functions f and g, which are optimal to minimize the reconstruction error, knowing that theta has been computed using the intensities. And this method is really used, for instance, for continuum cubes, but in our case, this is not the case, and we'll see that there are some problems. So to represent the difference between continuum cubes and line cubes, this is the example of a very common continuum cubes in hyperspectral imaging literature, which is Indian pines, and it have two examples of channels for Indian pines and for 13C08. What we can see is that there are a lot of similarities between the first channels and the second channels for Indian pines. That means that it looks like a compression will be possible, but it's not really the case for 13CO, because visually we can see that there is no such similarities. And in fact, more mathematically, if we compute we can compute that those images are independent in the statistical sense, which means that it is impossible to make a compressions. So in fact, it seems that applying this kind of method for line cubes is a real challenge, but I will show you that in fact it's more complicated, but not impossible. So to have a more quantitative idea of this problem, we can compute what's called the intrinsic dimension of Indian pines and 13CO, for instance. That means the optimal dimension the dimension of the bottleneck. So, for instance, we will use what is called the elbow method, which is used, for instance, for principal component analysis to find these optimal values. So we will plot the reconstruction error, which is the mean absolute deviation, which is like the mean square error, but not the square of the difference, just the absolute value of the difference, because it has nice property here. But anyway, and for Indian Pine, we can see that the reconstruction error is decreasing quickly at the beginning, but at the end, for a dimension of 4, it's like there is no real improvement if we increase the bottleneck size, which means that if we want to reduce the data set, we'll choose this dimension. For 13.0, this is not the case. And in fact, which has not this kind of elbow, which means that the intrinsic dimension of the signal is close to the extrinsic dimensions, which can be interpreted saying that there is no such lot of redundancies in the signal, and it will be complicated to encode the signal. So we have a lot of limitation, because that means that this kind of assumption is really useful for continuum cubes, but it's not the case for line cubes. And remember that the higher the intrinsic dimension is, the more complex is the signal extraction, because it means that there are no redundancies, a lot of redundancies in the signal. And what is really interesting is that this limitation applies not only for encoder neural networks, but for a whole kind of category of method, which is composed by, for instance, the PCA, principal component analysis, the autoencoder neural network, of course, and the low-rank tensor decompositions. This description applies to these whole categories. But at this stage, what is important is that this simple method that's used for continuum line cubes is impossible to use like this for line cube, but in fact is not impossible. And what we'll do is like a pact with the devil, because we'll try to sacrifice a little bit of signal fidelity in order to decrease the maximum of noise. And so we can, just in a nutshell, develop, for instance, 2 solutions. The first one is to adapt the network architecture to the data in order to fit what is really a line cube, and very different from continuum cubes. And the second one is to use prior knowledge in order to help the neural network to encode this signal. And so at the end, we obtain this kind of results for a given velocity channels. And these networks are called the local autoencoder with prior knowledge. And so it is very interesting, because in fact, just with some physical priors and physical information, we can change the method, which is not very useful, in order to create a method which is very useful to denoise the data, diminish the uncertainties and the signal values, and at the end, it's really easy to be processed for neural networks, and we lower the uncertainties on the parameters. And I'm done. Thank you.